All right, so welcome everybody. So this evening we're going to be going over, it's a continuation of our DeepSeek kind of deep dive, and we're going to be going through one section which was around the dual pipe. It's actually section 3, which is around infrastructure, so there's quite a bit associated with that.
Roger, which one of their many papers was this on?
So, I mean, we initially got kind of like the rest of the world got excited by their R1 release.
Right.
But I think we had noted that there was quite a bit of the innovation showed up in more detail in their earlier papers. And so the V3 is actually where they talked a lot about optimizations they did, scaling and stuff like that. R1, I think, was mostly just focused on using the reinforcement learning.
Okay.
So, all right, let's try this. I'm going to share that one. I don't think I'm going to need sound, but just in case. Let me know if that works for you.
It says I got it.
Okay. Okay. So the section, well, I originally called this dual pipe. This was kind of the part that got me interested. Is that big enough? Can you see? You can see it there.
It would be better if you could make it bigger.
Oh, let's see.
There you go.
Is that what you want?
Yeah.
Something weird is going on with the graphics, but yeah.
I've got little black rectangles.
Your Zoom windows are covering up portions of the screen.
Yeah,
Oh, there you go.
Let me just do.
Rendering, I think.
I think we did this the other time. That was kind of useful. Like that?
That's good. Yeah.
Okay. All right. So I think I got there. All right. So yeah, so it's about there was a particular graphics that showed up in the paper that kind of caught my eye, and that's where I started diving in on this. So these are some of the links. Again, it's not the R1, it's the DeepSeek V3 paper. I ended up diving into, there wasn't a lot of detail in the scheduling. So I ended up diving into this zero bubble paper, and it really did most kind of orientation until Ted today or yesterday introduced this ultra scale playbook, which covers a whole lot of like how do you scale up and train a really big network. A couple other links I had in here, less important. So before we get started, wanted to kind of talk about parallelism. And there's several types of parallelism that they use. So the idea is you have a model over here. You have a model that you're going to train. You're going to feed it data that represent here. And if it's on a single GPU, you feed it in. You do a forward pass, backwards pass. Actually, I guess parallelism applies to both training and inference, but it's all on one GPU. One way to get more performance is to do something called data parallelism, where essentially, instead of running the batch through one GPU, you run it through separate GPUs and just run some fraction, a micro batch, through each model. And then if you're in training mode, you do some consolidation of gradients and stuff like that. Tensor parallelism, a lot of these the transformer models deal with large matrix multiplications, and you can essentially break that up into, instead of one, n by n multiply, you can break it into something that's got kind of one column and one column against the entire matrix, or break it up even further if you want. So you break that large matrix multiply into pieces, spread the pieces out on a multi-GPU, and then once you've done the calculations, consolidate the results. And that's tensor parallelism. The one I started diving into was this pipeline parallelism. And so that kind of takes advantage of the fact that transformers tend to be layers of architecture. They happen to be identical layers, but it has that layering. So there's passing of activations from one layer to the next and gradients coming back down. But the rest is kind of all contained within that layer. And so that pipeline parallelism is the one that I'm going to dive into. That's what the zero bubble stuff mostly does. So is that any questions so far? Okay.
Hey, Roger, what is the definition of layer?
Oh, a layer in this context would be, one of the essentially a tension block and an MLP block and some norms in there. That's what they define as layer. Generally, the architectures I've seen, all the transformers have always have a tension and MLP in this, sometimes called FF, feed forward. Those always go 1-to-1. I don't know if that's necessary, but that's the way I've normally seen it. And that's what I'm calling a layer. That identical components then are repeated. So the output of one layer goes to the input of the next layer and up until you get, in the case of DeepSeek v3, 61 layers of that.
Hey, Rogers,
Yeah.
quick question. So both tensor parallelism and pipeline parallelism, the same data is going through all the GPUs, right? Just differently. Am I right?
Yeah. I mean, in this picture that I have here, they're all getting the same batch, so they're getting all the same data. But yeah, you're right. In the case of pipeline parallelism, so the batch will be sent in through this. There'll be some intermediate or hidden layer activations coming out of one layer that feed into the next layer. So it's actually, you might say that the input data is only fed into the first GPU. What
Right.
comes out of
Okay.
that is like an intermediate hidden layer that's sent to the next GPU, et cetera. Whereas in tensor parallelism, I think all of the GPUs get all of the incoming data, but when you're dealing with like a large matrix multiply, the weights will be distributed differently so that half of the weight matrix or one column of the weight matrix might be on GPU 0 and another column would be on GPU 1, et cetera. And
Right. Okay.
they have data flowing kind of between them. There's a scattered gather, or it's not the right term, it's something reduced, that happens before and after the tensor parallelism.
Okay.
Okay.
So then both of them basically handle the same amount of data. So I'm wondering, what's the advantage of one over the other?
A big part of it's communication. And then it is different data. I would say, like, for instance, in this data parallelism, there's less of the mini batch that's coming through each of the GPUs, but there's all of the weights of the model are on each GPU.
Right. So the data parallelism, I get that. I'm comparing the tensor and the pipeline, and I'm wondering, they both are at any given moment, they both are processing one batch of data, right? And so except that one is, horizontal, the other is vertical. And so from a data, like, throughput kind of perspective, I'm wondering if one is better than the other, or if there's any difference.
This will probably be one where we'll want to go through. Nihat, did you have a response to that?
Yeah, so what I was trying to say was like, so if you look at the evolution of these algorithms, the first algorithm to evolve was data parallelism. So the models could fit on a single node, a single GPU node, but they wanted to go through large amounts of data. So how is the way you scale the throughput up is like with data parallelism. But then they started hitting into roadblocks that a single model can't fit on a single node, on a single GPU node. So then they introduced this concept of tensor and pipeline parallelism. So Usually for throughput, you wouldn't use just tensor or just pipeline parallelism by itself. It would be coupled with data parallelism. But if you have a model which doesn't fit on a single GPU node, or sometimes even if the number of flops required are too much, you might split the model up into multiple machines. But I've never seen them use it individually. I've always seen them being used together, like tensor with data and pipeline with data, but they play different roles.
So Neha, do you know, so the question about when would I use tensor parallelism versus when would I use pipeline parallelism?
Yeah, so I'm just going to give a very intuitive answer. I'm not sure if this is correct. But I do believe tensor parallelism. So if one host has like 8 GPU nodes, you would use tensor parallelism across those 8 GPU nodes, but you wouldn't do across hosts. So pipeline parallelism comes into picture when you're actually doing across hosts. So you're like splitting up the model across different hosts.
Yeah, that makes sense.
Yeah.
Yeah, because in the case of, so I think this is an example of of tensor parallelism. So where they've split out this computation across 2 GPUs. So this is fundamentally one attention block.
Could you make it a bit bigger, please? If possible.
I don't know if I can.
Control wheel
Control
or
plus.
Yeah, control
plus.
plus, yeah.
Thank you.
Okay, let's see if we can find it again. Yeah, okay. So they've split the attention block, which we normally show as like one block in the diagram, and we split that across 2 GPUs. So we're all within one layer. And this operation then requires information flowing back and forth between these. So you spread it out, and then you're collecting the results. Whereas the pipeline, I believe the pipeline has a lesser communication requirement, internode communication requirement, because all you do is have the activations from one layer going to the next layer in the pipeline. So I think it's probably less communication.
In this case,
that makes sense.
And it's, Neha, so maybe this is also to your point, is that if you get to where your attention block, whatever your matrix is so big that it alone can't fit on a GPU,
Yeah.
then you have to go into tensor parallel.
Right.
So which brings the point in the picture that you had. I understand for the pipeline parallelism, it showed 8 batches somehow, and only 1 GPU or 4 GPUs. I don't understand why would you go high on the batches and then do pipeline parallelism versus maybe data parallelism by splitting the batches across multiple GPUs. You see that there is only that's one, and the second.
It's so you're talking about why do pipeline parallelism instead of data parallelism?
Right. So if you look at the pipeline parallelism, there is, I am assuming that picture below with the gray colors boxes is the batch size of 8.
Yep.
And if we are having trouble fitting in the pipeline on a single GPU or whichever way it is being split, why do we have to do pipeline parallelism versus data parallelism? Like maybe I
think the answer to these questions ends up being about compute, GPU memory, and inter-GPU communication. And we kind of have to dive deep into the details to understand that. The answer to the question here about data parallelism versus pipeline parallelism, if I'm doing pipeline or data parallelism, all of the gradient information needs to be consolidated between those and then redistributed, the model updates redistributed out to the model. So there's that level of communication. Whereas in the pipeline parallelism, all the gradient accumulation and even the optimizer information can all be stored on that local GPU. You don't have to copy it off off GPU. And the only thing that's being communicated is activations going forward during the forward pass and gradients on the backwards pass. So again, I think if you look at the communication, this is kind of good from a communication perspective. It can be intense from a memory perspective. You may not be able to fit it all on one GPU. And that's where you start doing things like Neha said, is you might actually do pipeline parallelism, but each of these layers, instead of being one GPU and multiple layers, might be tensor parallelized attention block, for instance, spread over multiple GPUs kind of horizontally, and those are then all stacked up in a pipeline parallel. So for instance, NVLink is faster than, what is it, IB and InfiniBand. So you might do up to 8 nodes. You could spread tensor parallelism, spread the attention block over that using NVLink, where you have higher communication requirements because these gradient updates, and then use InfiniBand through a series of these nodes using InfiniBand in a pipeline parallelism to fit a deeper model, a model that won't fit on just 8 GPUs.
Hey, Roger, if I could sort of just recap what you said. The original question was, when would you use tensor? When would you use pipeline parallelism? And I think the short answer is, if you're able to get away with it, you would not use tensor parallelism. You would always prefer pipeline parallelism. I think that's the simple answer. So if you can't get away with it, then you have to use multiple strategies. But between those two, I think because of what you said, the amount of communication, pipeline would be your choice. And if you're forced to use both, that's where both you and Neha pointed out that because there's higher communication, you want the nodes to be closer to each other. So if you have 8 GPUs, on a single server, then tensor parallelism between them is better than having tensor parallelism between 2 different boxes, for example. So
what I still am confused with is, let's say you need to do tensor parallelism or pipeline parallelism. Why would you go higher batch sizes when you can, like in tensor parallelism here, we are shown 4 GPUs with 8 batch across those, versus in pipeline parallelism, we are shown 8 batches across 4 GPUs. So essentially, is it always the 8 batches? And then the question still is that why would you go high on the batch?
I think Dave, you are reading into it too much. I think with if you have like data parallelism with 4 models, you could definitely do more batches, right? Like it's not about the batch here. It's just a question of what do I want to optimize for? So the question is, I want to optimize for throughput. My model fits into one machine and has decent flops, which I can manage. So how do I get more throughput? The best way is I want to go through this terabytes of data. So I need to process the data in parallel. Now, when I start processing the data in parallel, what happens is you have this async and sync strategies because you're basically training n models in parallel and you need to keep them in sync. You either start hitting a network limit where, say, suppose I have 100 models training in parallel, each had to communicate with each other, like all reduced kind of, all scattered reduced kind of operation. You start hitting your network bandwidth, or if you do async or some other form of data parallelism, it starts affecting model performance. So how do I not have more model training in parallel, but still have little bit more throughput and train a larger model together? So then you're like, okay, let me split up the model into multiple GPUs. So I can, while first GPU is working on some batch 1 to 10, the next GPU can work on like minus 10 to 0.
Right. I think you're right. I think what they're trying to show is that there is a batch size of 8, and how you distribute it across single GPU in the first column versus 4 GPUs,
Yeah.
and they're not trying to. You're right. Maybe I'm reading too much into
Yeah,
this.
you're
Yeah.
reading too much into the diagram. Yeah, it
Yeah.
doesn't indicate performance. Yeah, yeah.
The important thing is to understand data parallelism splits up the batch. Okay. The rest of them that they all have size 8 is not, yeah, don't read too much into it. But at the end of the day, Dave, I think you're asking the question about, I answered the previous question about pipeline versus tensor parallelism. You would prefer pipeline parallelism. When it comes to
definitely.
pipeline parallelism versus data parallelism, I don't know well enough the answer, but I suspect that you may be better off with pipeline parallelism as well. And if that's the case, then you would, if you have a 61 layer model and you have a bajillion GPUs, you might actually prefer to have 61 different GPUs processing layers and then fit as large a batch per GPU as you can. If in fact pipeline is more efficient than data parallelism.
Yeah, I don't know. I mean, I would go, my intuition was the other way, but again, let's not maybe hold the discussion here. But
but that's the simple answer is it's the communication. Okay. If data parallelism is better, then you would do exactly that. You would cram as many layers as you can on each GPU and have as small a batch size, in order to cram as many layers, right? So that's the answer.
Right. My thinking was that I would like to use data parallelism because that way I have no communication for a single batch across GPUs, and I get all the information on the single GPU, and all I have to do is the accumulation.
It isn't no.
Well, I still have to. Oh, you think there will be no communication for the gradient accumulation?
No. I'm saying you have to accumulate all of your parameter updates.
Right. For gradient
accumulate. Yeah, you have to consolidate. You have to reduce your gradient accumulation, and then update. Your optimizer needs to update the weights. And
and I think one other thing is expensive.
One other thing is that again, these aren't mutually exclusive. You can be doing all of these and more actually. There's also sequence parallelism that you can do as well. So they're all pieces that you can keep adding so that you can handle bigger and bigger models. If it fits on one GPU, then that's the easiest. It seems like data parallelism, the model has to fit on one GPU, and it seems like that is the most common. I don't know, Ted, like you, I'm not sure that data parallelism is better than pipeline parallelism, but it seems to be more common.
It just came in earlier. That's why models started becoming bigger later, but data started becoming bigger first.
Yes, data parallelism is an easy one if you just have a tiny model and it fits on your GPU.
Because you just copy the model across all the different GPUs. So it's just like the same one and you run it all in parallel.
Yes. But the other side effect of having a tiny model that fits on a GPU is that the number of parameters is relatively small. So then the gradient accumulation and optimizer step is also small. So that's why it's not necessarily analogous. But I think we all are in agreement that tensor parallelism is the worst, and that you're going to do whichever one has the least amount of communication between GPUs, because that's what slows it down.
Yeah. Okay, let's see. Shulin, you had a question, but it looks like you've lowered your hand.
Yeah, Richard's picture saw my questions.
Okay, great. So let's see. So that's 20 minutes into the first slide. That's not good.
That's pretty classic.
All right.
Sorry to have started it all.
No, don't apologize. That's the point of the group.
Yeah, that's why we enjoy it, actually.
You've been here a while, Roger. You should know better than that. That's past.
Jan, you're the spammer. We need to identify you up front.
Oh, no.
All right. So let's see. So this is the section then that I kind of dived into on this V3 paper, which is the infrastructures. There's some other interesting stuff that we may or may not get to in the paper, but this was the one I was going to cover. So let's see. I looked at a little bit of through the architecture. Okay, so the 2000 NVIDIA's H800s. I don't know the exact size of an H800, but that's pretty small by comparison to some of the larger. What was it? The X's latest one came out at 100,000, or are they up to 200,000 GPUs now? Anyhow, that
100,000, I think.
No,
Yeah.
it's 200. It's 200,000 because they're talking about going to 1 million, which is 5 times the energy cost. So people are reducing
Right.
1 million that way.
Yeah. Okay, anyhow, so and the nodes are they end up having 8 GPUs per node. You can link those 8 GPUs with NVLink. And I had seen something here. NVLink was, I think they reference 160. It's not there. 160 gigabytes per second. Which was, I think, only like NVLink 2. NVLink 5 can go up to 1,800 gigabytes a second. And then the InfiniBand was like a fifth of that about in terms of bandwidth. This figure here is very interesting. So we're going to be looking through this zero bubble paper and diving into it more. But basically, the thing you want to look at here is that there's computation and communication, and they've separated it out into multiple pieces. And by looking at it in multiple pieces, you can start to look at how you can schedule across these multiple GPUs, particularly in the pipeline parallel. So they have the MLP portion and the attention portion, and then let's see, this is the forward pass, and then these are the backward passes. And then I think the red bars represent like synchronization between the nodes. And then in parallel, they're doing the dispatch, both forward and let's see, pipeline parallel. I think this is the where they're doing reduces here. This would probably be the gradients moving in a forward direction, or excuse me, the activations in the
Hey,
forward.
Roger, sorry to interrupt. Could you zoom out the full width of the PDF, please?
Yeah, let's see. How's that?
One more, maybe. Yeah.
Okay.
Thank you.
Yeah, so here they're just talking about forward and backwards. So again, I think it's activations forward and gradients backwards. And I think some of this is dispatch combined. So this is where they're sending it out to multiple nodes and back. And we'll look at that a little bit. I don't think they use tensor parallel, but they do use expert parallel. So we'll look at how that works. So here's some of the things that they had in the framework. I could not find this framework. I think, it's crafted by engineers from the ground up, and I didn't see anything where that had been published.
I'm pretty sure that's like in China, like it's like their proprietary stuff.
Right. Okay. That's kind of what I gathered. But a lot of the stuff that they have built into this is stuff that is building, on other works. So and they're very open about it, and they've really used it quite well. So pipeline parallel, we'll look at that in the zero bubble stuff. Export parallel, I think I had a link here where I was looking at. Well, I'm going to come back to that actually. Let me.
That's just spreading the experts across multiple nodes.
Right. So the idea is, since you have they have actually 256 experts, and I think they activate 8 on each pass, 9 because they have one local, and then they have 8 nodes that they spread that across. So they essentially each node is responsible for its set of experts, and everybody shares those. So they'll communicate the activation over to that expert and bring the results back. And then 01, this is for the optimizer. The state for the optimizer is essentially kind of sharded across multiple nodes. So that's another technique. So again, they're borrowing techniques that are already out there. Part of this kind of blew my mind when I first saw it, but I think that a lot of it is stuff the work has already existed out there. Janeth?
Does NVLink do both within a host and across hosts?
I
think it's
don't.
physical cards because it's like a cord, right?
Right. Yeah, Richard, I have never seen one, so you're going to be better on this, but I did do a little searching, and it looks like it can handle 8 nodes, and it's typically within so you have one computer, one CPU with 8 GPUs connected, and all 8 of those would be connected through NVLink within kind of that chassis.
That is correct. So NVLink is limited to a single node, and then across nodes will be InfiniBand or whatever it was before InfiniBand. And within the node, like you can, NVLink is supported for the server grade GPUs, or I shouldn't call them GPUs for machine learning, but it's supported at the level of consumer grade GPUs, 3090s. It may have limit on how many you can put in parallel on a consumer grade to the workstation grade, which is ADA 6000 or 6000 or whatever it's called for different generations. And then the A100 and H100, which is the server grade. And there it can go up to 8, if I'm not mistaken.
Richard, is that?
I don't think that after the A6000s, they stopped doing it on all their cards, at least as far as I'm aware. Yeah, all the H100s and 200s I've ever worked with, we couldn't NV-link them together because it just doesn't have it anymore.
Oh, really?
I thought for the 40 series, which is the H100 series server side, right? They did not support it at the consumer grade levels and maybe even at the workstation grade level, but they do support at the H100 levels.
Oh, okay. I'll double check with my guy, but yeah, we didn't have the NV-link on ours, which was it didn't really hamper anything that much, just because the communications were already like really fast anyway, because it was all on bare metal. But yeah, from my understanding, it definitely for sure in the consumer grade cards, like after the 3800s, there's just no NV links at all.
Yeah, I'm pretty sure of the consumer grade cards because when I was making my machine of 4090s, they had removed that, and there were several bugs in even trying to run data parallelism or other kinds of parallelism on the early CUDA libraries and the drivers they had.
So this page I had asked Gemini, and that's consistent with what you're saying, Dave, is that the 3090 they stopped it and felt like the PCIe had enough bandwidth. But I think the data center ones, it's still saying like H100, A100, those all still have it.
I have a question on the paper that you had. So where it said 16-way pipeline parallelism, 64-way MOE parallelism, and something else for the data parallelism on the paper.
Yep.
So could you elaborate what those ways mean? Like, does it mean that they have 16 GPUs to fit in the whole model? Or whichever way they decided to, I mean, it could be less than that, but for batches and other things, they may have more.
Hey, Dave, I wanted to go through the zero bubble paper first. Can you hold that question? We'll come back to it.
Okay.
Yeah, I've got a slide that kind of covers that. And we'll need a different picture to describe what a mixture of expert is. Neha, did you have something you wanted to add?
Oh, I was just going to say about the NVLink stuff. The Llama 3 herd of models paper also talks about NVLink, so it was definitely present for H100.
Okay.
Yeah.
Okay, great. Okay, so I think I'll switch over then at this point to the other paper. So the picture that kind of blew my mind and I didn't know how to interpret it was this one, figure 5. Just trying to figure out how to even read it. But as I dived into it more, like I said, this zero bubble was probably the best paper on it. So zero bubble, the first thing to kind of know about this is that when you're training a model like this, you have a forward pass. All these MLPs are big matrix multiplies. There's other operations in there, an RMS norm and softmax and stuff like that. They have a little bit different, but some of the heaviest weight is in these matrix multiplies. So this picture captures what that looks like and what the difference is between the forward pass and the backwards pass. And that's something I didn't really understand before. So forward pass, you have your activation from maybe the embedding layer or maybe the next, the previous layer. If you're in one of the intermediate layers, the activation comes in. You'll multiply the activation times your local weight matrix, and the output of that then goes through some sort of activation function, and then you get Y, in this case they're calling it, which is the forward pass, and then that moves on to the next layer. That's kind of what we see all the time in describing it. And in the backward pass, there's actually, we can think of this as the gradient with respect to Y of the loss. So that's the gradient flowing backwards down the stack. And because of this matrix, oh no, this actually is, yeah, this is the matrix multiply in here. And you get gradient with the loss flows into the weights. Yeah, here. So the gradient flows in two directions. One is it's the gradient of the loss with respect to the input. Do I need to get bigger again? So going through this direction, the gradient of the loss with respect to the input flows to the next previous layer. So that's what they call the backwards gradient that I think they called it B in the diagrams later on here. But it also flows into the weight. The weight is the part that we normally, the gradient of the loss with respect to, okay, now I understand what's going on here. This is the gradient of the output with respect to the loss with respect to Y. This sigma function sends the same value in two directions. That's why I was getting confused, but it's basically the same value. That's the gradient of the loss with respect to this internal Z layer. And then they flow it through the matrix multiply. The gradient of the input with, or the loss with respect to the input goes this way. And then they also go this direction into the weights. So what you get on the output is the gradient of the loss with respect to the weights. That is the gradient accumulation that they'll be doing. So there's two flows. So a little bit of work here, but twice as much work or more going this direction. And part of it flows to the previous layer, part of it flows directly into the weights. So I kind of stumbled a little bit there, but was that clear enough? Any questions on that?
I probably would also like to add that in terms of the memory requirements, the backward pass, depending on the optimizer, may have more requirements for memory than the forward pass because of extra states.
Much bigger. Yeah, one of the things we have is a really good picture from the post that Ted gave, shows that memory footprint. I kept this from an earlier slide that I'd done just so we can capture that. Again, what happens is in the forward pass, you've got the input to each layer and the output, and it just keeps getting passed up through all of the layers of the model. You compute the gradient, the loss function, and that generates the gradient that flows all the way back. This arrow really isn't a data movement. It's just using the weight. The activations are saved in this layer and will be used in this layer to generate the gradients, the updates to the gradient into the weight, the gradient accumulation for the weights in each one of these layers. So for the backwards, you got the gradient flowing in. You've got the activations you used previously. Use the two of those to propagate the gradient to the next layer, but also to propagate the gradient into the weights. So it's stacked like that. Okay. Yeah, and here they express it essentially that same function. Let's see. They're calling it B and W, and this in this zero bubble, they said, okay, there's actually a paper before, oh darn, I don't have a link to that, but this 1F, 1B, where they didn't separate the forward and backwards into two pieces. These guys, the main thing that they added in this paper is that they realized that there's two flows here, one calculation that flows to the previous layer, one that flows into the weights. And those don't necessarily have to be done at the same time. They're separate matrix multiplies. They could be done at separate time. And they use that, they take advantage of that here. So in this previous one forward, one back algorithm, so if I'm doing pipeline parallel, then I'm going to, again, like this picture, I'm going to be, let's say this would be a pipeline of 4, where each, if I drew, GPU boundaries around each of these columns here, this GPU is handling this layer, propagating on, et cetera, through. This is showing a timeline of these 4 GPUs and what they're doing, what they're processing at a time. If you were completely naive, you would send an input to the next layer, do nothing, and wait until you got the backward propagation coming back. So you could imagine just, if you just look at these ones coming down and ones going up, you can imagine that's the most naive way to use a pipeline. But once the first GPU is handled processing of the first layer on the first, what they'll call micro batches. So they take mini batches and break them into smaller pieces so that they can process these smaller pieces in parallel. Once it's finished its micro batch, the first micro batch, and it sends on to the next layer, it actually can start working on the next micro batch. And so all of these can be running in parallel. Once you get to the top of this and you calculate your loss function, now you have your gradient that you can flow backwards. And so in the 1F, 1B paper, this operation took longer because you were doing two things. You were propagating into your weights and you were propagating into is that big enough? I don't know if I can go too much bigger. So you had to wait until you got this guy processed, took longer before you could get the previous one, previous layer, the next lower layer going. So in 1F, 1B, they just had them together. Notice that there's idle time. So this is what they call bubbles. Bubbles are these little gray spots where the GPU is not doing anything. And there's bubbles on the front end. Once you get into this middle stage, this is kind of the warm-up bubble, and this is the cool-down bubble. Once you get into the middle, you can, as many micro batches as you're going to process together, you're kind of steady state. You can, if you got things scheduled right, you can just keep everything busy. But then you have to wait for this optimizer step where we do, accumulate all the gradients from everybody and apply your atom algorithm or whatever it is, update your weights, and then you get started over here. You start over again with another warm-up bubble. Any questions on the 1F, 1B? Okay, so what these guys did is they said, you know what? This path here, this flow of the gradient here, until I can do that, the previous GPU can't do anything. But these don't have to be coupled, so I could actually do these separate. So let me prioritize getting this B back to the next prior level, and I'll worry about my W update, my weight update. I can postpone that and do that later. And so that's what this algorithm is. So as soon as we get, I've got 3 colors now. I've got a forward pass, the B pass backward flow, and the weight backward flow. And I can prioritize these gradient backward flows. As soon as I get that up to the top level, I can start sending it back down through the layers. I do all of that. Once I have sent those, I can start processing my weights later. Oops, let me do this one first. Once I've got all the ones going backwards, then I can start intermixing the weight updates. And again, I'm in a steady state in the middle. On the warm-up, I've got these bubbles. And then out here, I'm essentially filling this, what used to be this bubble back here, I'm kind of filling this with leftover weight updates. And then everybody does their optimizer updates at this point. So that was the zero bubble H1. In H2, so this is different than what they did in the DeepSeek paper, but in H2, it's kind of, but I thought it was really an interesting technique. They said, you know what, these layers are more or less independent. Let me go ahead and just do my optimizer steps in a non-synchronized fashion. I can start updating, do an optimizer step just for this layer here, and that way I get rid of these cooldown bubbles. And I get to where, at this point now, I've got all of the only bubbles I get is this initial startup bubble. I can keep doing multiple mini batch updates without any bubble. Yeah, Neha.
Yeah, I think there is one more aspect to this, which is the memory. Because after you do the W, you can lose those activations, but you can't lose those activations until you do the green box. So if you delay the green box too much into the future, then your memory utilization will keep increasing.
Yeah, that's correct. And that's the part that they referenced later on. You're absolutely right. And this is the thing that they're quantizing what is the amount of memory being used. So this is one. So I didn't understand, like, where the heck did this come from? So I jumped down to another paper that they referenced. This paper is actually about recomputing. So it's another way to kind of reduce footprint of the memory. You recompute your activations, but they did introduce the terminologies that they have. So they have vocabulary size, sequence length that you can support, hidden dimension size, and micro batch size, et cetera. So they define these terms, and then they go through using kind of a standard transformer architecture. Say, what are the pieces that are in here? And that, and this is pretty standard, I think. It's a little different for a mixture of experts, but mixture of experts is mostly like an MLP. And then they go through and said, okay, so when you're doing back propagation, as you pointed out, Neha, part of this process, where'd that go? Oops.
Sorry, Roger, can you increase the size again, please?
Pardon me?
For the other papers that you bring up,
yeah, okay.
if you don't mind increasing the size, thanks.
Yeah, I will when I get back to those. For this process, you essentially have to wait, let's see, that propagating into the input, you multiply, oh yeah, it's right there, the weight matrix times the activation, this activation. And then propagating into the weights, you have to propagate, let's see, the XT, so the input activations times that. So you have to hang on to these activations because there's a matrix multiplying both directions. And what are you saying? This activation is the one that you have to hang on to?
So Roger, in your diagram above that horizontal line, you have the gradient. You have that gradient of L. No, above the horizontal. Yeah, right there.
Yeah.
That, if you wait to do the W, you have to store that.
Oh, you have to hang on to that. Fair enough.
Yeah.
Fair enough. Yep. Okay. So where was I? Okay. So in here, they're saying for a standard transformer, how much make it?
The width, please.
For each of these functions that you're propagating the gradient back through, there's potential for some of this activation that you have to hang on to. And it's true for these matrix multiplies. It's also true for softmax, and also even for dropouts, because you need to keep track of which activations were dropped out. And so they have the equation that they've gone through all of those. And in the end, they come up with this 34 plus 5 AS thing. So that was, I hadn't thought about how much activation you need to hang on to at each layer, but that is how they came up with that number, these crazy numbers for memory. And again, that's assuming that specific architecture. And it's going to be different if you have like MOE or different activations or something like that. Okay. How are we doing time-wise? 7:35. Okay. So more I want to cover in this. Talk about memory size. Oh yeah, we were talking about memory. So this is the memory requirements for each of these, but you have to hang on to it. So one of the deals here is that I have to hang on to the activations from this level until I get these gradients done back here. Gradient calculations done right there. So, you know, if you imagine this is 4 devices, let's imagine that it's 8 devices, then that's going to be eight times as long. So whatever my activation is, I'm having to hang on to it for 8 cycles because I've got to wait for this stuff to come all the way back. It's actually probably 16, is it? Because I got to go all the way down and then all the way back. So it's probably 16 cycles before it gets back. So when you're doing this, the more distance you have between the forward pass and the backwards pass, the more memory footprint you're going to have to store, hang on to for activations. Does that make sense? Neha, that kind of was the point you were trying to make. So,
Yeah.
So there's that aspect of how long do you need to hang on to it. This was an analysis of how big are the bubbles, and I am going to, the one thing, this is again not in the paper, but I thought it was kind of cool thing. The way they could do this kind of non-synchronized optimizer step is that they assume that there's no global context or state that is going to affect the optimizer at its level. And it turns out that's not entirely true, I guess. I think they talked about, here we go. Sometimes they don't do an update if a NAN is spotted, or if they get gradient clipping. So it can affect that. So rather than wait till everything's together, do the calculation and see if there was a global interaction of some sort, they just assume that they can get started locally. And then what would happen is when the gradient came back, if there was something that had gone, had modified what the optimizer would have done that was global, they would essentially do a rollback. Now, I couldn't find whether that means just throw away these forward passes or redo these forward passes. But whatever it was, they did say that they noticed most of the time the global state has no effect, and it's rarely triggered. So it was effective, even if you have a rollback that costs time. It was effective to just ignore the update and then get rid of the bubble and just do these asynchronous ones. So I don't know why they didn't use this. It seems like a pretty cool algorithm, but
Roger, they mention it there in the paragraph above the diagram. Upon receipt, sometimes they do a rollback. If an amendment to the gradient is required, a rollback will be issued, but it happens so less frequently that it doesn't.
Yeah, so Neha, the part I didn't understand is what does it mean to do a rollback? Like what happens to these calculations here that were done using an improperly updated set of weights?
So I believe what they do is they lose the calculations basically.
They just throw those away.
Yeah, that's what I think. Yeah.
So if I'm not mistaken, that blue in the first row is the next batch, right? Because 8765 is for the previous batch.
It's it's forward pass for the next
batch.
For the next set of micro batches.
Right. So why should that be affected? That should continue. It's just that the previous micro batch.
No, because it would have been, the weights were updated here, right? Locally at this layer. they were updated, and these calculations would have been done using the updated weights. But there was something down here that blew up that says, no, we didn't mean to update our weights. So these were done with the wrong weights. So the little red bar, I read someplace where it actually was doing the like roll back the updates, but it didn't. I never saw what they do with the calculations that went through ahead of time. If they just
I'm a little confused with this picture. In the previous picture that you had, these yellow boxes. Oh no, it is the way it is. I was mistaken. Yeah.
There's two different approaches.
Yeah, so I think the point Roger is trying to make is, say suppose device 1 already processed batch 1 and 2, and then device 3, oh, you scroll down the picture. Yeah. Yeah, and then the device 3 tries to update the optimizer and it realizes something is wrong here. So it will just lose the batch on device 1, it will lose the 1 and 2 batches it has already processed. The first 2 blue boxes, and on device 2 it will lose 1 blue box. So in the worst case scenario, you would lose like 3 blue boxes on the first, 2 on the second, and 1 on the third, because by then you'll realize if something is wrong.
Yeah. Anyhow, interesting, and they get down to zero bubble with that, which is what the paper is about. So that was all kind of cool. So they then introduce one more thing that I'm going to talk about, because this isn't something that they did. This is the V schedule, zero buffer or zero bubble V schedule. So the thing they did here is they realized, I think it's motivated by memory footprint. So the first layers have to hang on to their activation longer, right? Because they're going to have to wait until the gradient has gone all the way to the loss function and come back. Whereas the ones in the middle don't have to hold on as long, because it takes less time for the gradient to get back. And the ones very near the top, device 4 in this case, which is on the bottom, those are, that turns around right away. And so there was a disparity in the amount of memory required on each of these. And so what happened is they came up with a W schedule where it's a little harder to follow because it goes kind of crazy here, but the W, or excuse me, the V, I said W, I meant V. The forward pass goes all the way down to device 4 and then back up to device 1. And then the backwards pass goes back down to device 4, and then wherever the green is, back to device 1. So essentially, device 1 is both the first layer and the last layer. So it has a big memory footprint for the first layer because the activations it has to hang on to for 8 cycles. And it's got a small footprint for the last one because it can turn it around right away. Whereas the one device 4, it has the middle 2 layers, both of which are hung on to for about half the time. And so what it does is it equalizes the memory footprint between those two. But it does require a little bit more communication because the activations have to go through essentially 8 layers to get to the loss function, whereas before it was only 4. But the memory is more equalized over the GPUs. Does that make sense? Do I need to go over that? Is that clear enough? Okay. In that case, I'm going to go back to... Yeah.
So in a sense, this is equivalent to like a GPU with 8 times the memory, is it? I mean, forget about the latency and the lagging because of the communication, but from a memory footprint perspective, is that what this ends up becoming?
No, it's more like in this case, in the first case they did, you would have looked at this and said, okay, because this guy, boy, it's quite a ways back there, because this guy is in the first layer, he has to hold on to, before he can do the backward pass, he has to wait, 8 times before the gradient gets back to him, right?
Right.
Whereas this one only had to, let's see, that had 7 between it. This has only whatever it is, 4 between it. This only has 2 between it. So this guy is going to be using, 5 times, 7 times more memory for holding on to those activations than the bottom one. Whereas in this zero bubble V, essentially all of the GPUs are consuming the equivalent, an equal amount of memory, because one is holding it, for 7, half of it for 7 and half for 1. The other one's holding half for 5 and half for 2, type of thing. And so they all have the same type of memory footprint, activation memory footprint.
I see. Okay, thanks.
So that's, again, it addresses the memory issue, and they're still using this asynchronous optimizer update. Looks to me to be a pretty cool schedule. I can now get into this picture. We can understand this picture a little bit better now, because you can see these are going down through 8 devices before the gradient starts coming back up. They have split the backwards gradient and the, the backwards for weight and backwards for input. They have scheduled.
Hey, Roger, may I ask you to please increase the.
Yeah. So they did, take inspiration from the zero bubble. Well, actually, I don't know if they got it from zero bubble, but they did separate the 2 backward phases so that they could, send the backwards for input as quickly as possible, and then the backwards for late weights can be later. But they didn't do out here. They didn't do the sliding update. I think this reaches a steady state, although when I look at it, I'm not quite sure why these are all left, why those wouldn't have been scheduled into these holes. The blue ones out here, I'm not sure why they didn't fill these holes with these blue guys. But I kind of assume there must be a steady state mode that they can get in where these weight updates are filling in these holes and they can run steady state. But the one other thing that they did, so that makes it a dual pipe instead of the zero bubble, is that they chose to send one pass starting from device 0 down to device 7. And then you can see it comes back up. But they also, at the same time, started first layer at device 7 and sent it up to device 0. So device 0 is both a layer 0, the first layer and the last layer. But it's for essentially, it's the first and the last, because it's got a handle for the ones that are going this direction, it's first. For the ones going this direction, it's going to be the last layer on the stack. That reduced this bubble size is what I believe they mentioned. That's where they're looking. The bubble size they reduce here. So it's PP over 2 because instead of having a triangle that goes all the way down here, they have just this triangle space. That space is PP over 2. But they had to store twice as many parameters because this guy is both the bottom and the top. This guy down here is also the bottom and the top. So the parameters are stored twice, if that makes sense. And they get the reduced bubble, but it's at the cost of having the parameters twice. And to me, that at first didn't make sense. But if I go back to, let's see, I thought I copied that over here. Maybe I didn't copy it over. This is a slide from the scaling blog.
The Hugging Face ultra scale, yeah.
Yeah, ultra scale. What I didn't think about is how much, when I guess I thought about GPU size relative to parameter count mostly. I hadn't really taken into account these activations that you have to hang on to for the backward pass. So this is a profile from Llama 1B, and they show here, so the blue down here, I believe, is parameter space. The purple is all of the activations. And this pink is the optimizer state. And so, out of this whatever it is, 65 GPU peak, they're only a small fraction. This must be 2. It looks a little bit bigger than 1 billion, 1 gigabyte. So it's probably using shorts. So it's at least 2. But anyhow, the ratio is what's important here, is that a little bit of parameter, a lot of activation, and quite a bit of optimizer state. So I didn't understand how much you had to worry about the activation. In this paper, and when they did the dual pipe, they essentially said that, you know what, we don't store, their MLP is, since they only, we haven't really covered how MLP optimization works. In MLP, you typically have a feed-forward network like this. In the case of MLP, they're showing it, adding it as an extra layer. I think actually in DeepSeek, they replaced the feed-forward network with the MLP, or with the mixture of experts. They have one dedicated one, which stays always selected, and then they have 256 that you select 8 of. But anyhow, when you do parallel, they will have multiple nodes. Like when you have the MOA data, what do they call it? MOA data parallel 64 expert. I think what it is they have a total of 256 of these separate feed-forward networks that they're selecting from. Those are the experts. And each time they go through, they will select 8 of them. And I think that the 64, Dave, you asked the question earlier. I think that is that they have 8 nodes. Each node has 8 GPUs, so that's 64 GPUs total. And this is spread, these feed-forward networks of the MOE are spread over the 64 GPUs. So when you're doing a forward pass on the MOE, it'll come to some level, it'll decide which experts you're going to activate for this particular hidden state. And then you will route them to all the appropriate node, the appropriate GPU that handles that particular expert. You'll do the feed-forward calculation, and then you'll go and retrieve the results from those all of your experts back into your stream, residual stream. So the point is that at least the MLP portion of this is actually pretty small when you have it spread over 64 nodes. And so that parameter count, that blue part, was it at the bottom? That's relatively small. And so they could actually afford in this mode, even though they were requiring to store twice as many parameters as they normally would, because you have, again, both the first and the last layer in each of these 2 devices, device 0 and device 7. You had to store the parameter twice, but your memory footprint is going to be, actually, does it change the memory footprint? It doesn't change the memory footprint, but it does reduce your bubble. So,
hey, Roger,
this was an acceptable choice. Yeah.
I think in the end, it might be a little bit simpler than that. So what's often not explicit in vanilla diagrams that you see that show what the attention architect, what an LLM looks like, right, is the fact that the weights are conceptually copied to every token position. Okay, they're not physically copied, but they're conceptually copied and they're shared across every token position. So the ultrascaling long article talks about this. And so basically, if you have a model and you have a max length of 4K, and the weights are whatever, 4 billion 32-bit floats, then you need, I said 1 billion, right? 1 billion 32-bit floats, then you need 4 gigabytes to store all these weights. And you have 4,000 activations, so to speak, for every weight. When you up that sequence length to 32,000, now you have 32,000 activations for, each set of weights. And the DeepSeek V3 was sequence length 128,000.
Yeah, actually, they trained it sequence length 4K though. They expanded it later
until the very end.
Yeah, they grew it in the end. They grew it to you do it.
Okay.
You change your rope and bedding, and then you do a little fine tuning on it. But most of the training was at 4K. But still, 4K, it makes this really big. It's the activations end up being really big.
Yes.
Relative to the parameter.
For every set of weights, you have basically 4,000 activations.
Yes. Yeah.
And so at the end of the day, the bottom teal blue and the pink above it get to be relatively small, and doubling that is not that big a deal.
Yeah.
I think that's the bottom line.
Well, that's one aspect. Yeah. The mixture of expert parallelism means this blue line is smaller.
I don't think so. It just means it's spread over multiple physical nodes, but it's the same size.
No, because each node only handles eight experts.
Yeah, that's what I'm saying. It's still 671 billion parameters. It's just spread over more nodes because of this 64-way parallelism. But at the end of the day, it's still the same.
Yeah, well, of course, yeah. And then the activations, or the optimizers, they spread those also. It probably doesn't matter for the mixture of expert portion, but for the attention blocks, they spread those. That's what the zero.
Yeah, the optimizer, it's always just going to be two optimizer variables for every parameter.
Right, but for the ones where you have the weight spread out, so if you're doing attention on multiple ones, you can spread. I'm pretty sure they reference zero was one of the techniques that they used. Yep, 0-1 parallelism. So this is where they spread the optimizer, so you don't have redundant optimizer states on each of the nodes. You only store that on once. So again,
Roger,
the
activation size is probably also bigger because of the floating point unit chosen for that. Like there are 32 bits versus weights are 8 bits and so on and so forth. Is that also a factor?
Yeah.
SFP versus FP32?
I mean, it's not captured here, but yeah, that you're right. They have more weight. This is just one like I said, I was trying to compute what these numbers would actually be for the DeepSeek V3, but I just couldn't do it. So I just captured this as just kind of a scale of, as Ted said, remember that your activations become much bigger than than your parameter, and your optimizer state is actually bigger than your parameter as well. So when you think about this stuff fitting on GPU, it's not parameters that are the limiting factors. It's optimizer and, more important, the activations.
Okay, and this one is Llama 1B, so of course this is not even DeepSeek.
Yeah, exactly.
Yeah. And that pattern is only true for language models where you have weights shared across token positions. So if you were doing something like computer vision and you had a ResNet 50 versus a ResNet 151, you would not see this pattern. You would see that memory usage is almost linear with number of parameters in your ResNet model.
Yeah, that was the thing that Ted, was not intuitive to me. I didn't realize how much of an issue the activations were, memory footprint.
Yeah.
And you're right.
Yeah.
It's because you can think of it as that way to share it against all tokens in the sequence.
Yep.
So
you got a hand raised.
Yeah, Gina?
Yeah, so I'm wondering which of these are like proportional to the number of tokens, in the context window. Is it the purple is, right?
The purple,
The
I
light.
think, certainly is, yeah.
And
Yeah, because the activations, you'll have more activations for a longer sequence, and it grows.
Right.
It grows quadratically, maybe, or is that grows linear?
Linearly.
Linear, okay. So, if we imagine doubling the context window so that the purple will double, will anything else change?
The orange is going to grow a little bit depending on what the intermediate steps you use to keep track of your gradients. But the main point is the pink and the blue at the bottom do not grow.
Right.
And that's why they do the thing that Roger said is they pick a smaller sequence length like 4,000 that they do 98% of their training. Because
and then
it
they
just
do the
would
rope
become
scale.
so much crazier expensive to do the whole thing at a longer sequence length.
Right. Cool. Thanks.
Any more on that? Let me, I think those were the main things we talked about, the zero parallelism, basically optimizer parallelism, the mixture of expert stuff, pipeline. I think we got it all here. I had some section I was going to talk about. I won't, it's time, we don't really have time to do it right now, but I did notice this I hadn't captured before. So they do it without the costly tensor parallelism. That's getting back to our conversation in the beginning, Ted. This was if you can avoid tensor parallelism, you do. But the thing that I didn't find elsewhere that seems like innovative here was this using the they wrote their kernels, wrote special kernels so that they could do these communication between the nodes on the NVLink and InfiniBand concurrent with the computation. So the scheduling and the actually execution of that was all done in parallel. I don't know, has anybody heard of any other work in that area where they've been doing overlapping of the computation?
So whenever you end up doing any custom implementation where you are bypassing the default mapping for your units of work to the SMs, if you may, in a thread cluster, then you have to maybe go one level lower than the CUDA scheduler and the allocator level. Then you would do that. But otherwise, much of it is in a typical scenario between PyTorch and the CUDA layers handled internally by the compiler and the lower layers.
Yeah, that's the thing. So they talk about doing, what did they say? I thought they talked about developed efficient cross-node and all communication kernels. But from what I understood, I did see actually where like the Accelerate package claimed to be doing concurrent calculation and communication. So I
Roger,
don't know how innovative
they're all doing that.
Are they? Okay. So then I don't know what this means.
No. So just imagine that you have a regular computer. It's not a GPU. Okay. And your regular computer is doing two things. It's, I don't know, doing the graphical interface for the user, and it's doing database queries. Okay. And you can have threads that are doing both of those things. Okay. Except NVIDIA wrote your software and they gave you 6 threads for the GUI and they gave you 10 threads for the database. And if that's not exactly the ratio that you need, you're up the creek because now you're going to have idle threads wasted for one of them. So what they said is that they figured out exactly what the break-even point was, and they split those those 16 threads exactly the way they needed instead of just the predefined NVIDIA 6 and 10.
Gotcha. Okay.
Everybody's doing a version of parallel. It's just, but if you don't get them balanced exactly right, you're going to have somebody waiting.
They used FP8, so they had different workload
Got it.
distribution, so they had to come up with more optimizations.
Okay. That makes a lot of sense. Thanks, Ted. That's cool. Okay. Is there anything else? I don't think so. I think that's the most of it. So yep, just flipping through. I think we're pretty much done. There's the GPU stuff that we just don't have time to dive into. We can maybe do that later. But anyhow, that was my deep dive into the dual pipe, and it was a pretty fun journey.
Nice job, Roger.
Thanks. So that brings up that paper. So again, this is where, I mean, there's a few more things in the DeepSeek. The multi-token prediction is a little bit of an interesting thing. Ted, I don't know if there's any other areas that you thought were worthy of discussion in.
No, I think multi-token, we've talked about the latent attention and the 8-bit and this mixture of experts. We haven't really talked about their more aggressive mixture of experts.
Okay.
So theoretically, we could talk a little bit about that if we want, or if we want to move on, like other papers or something.
I was definitely very interested in Ted's views on the what is it called?
Fallacies.
DeepSeek
fallacies.
Yeah, I used some other word, but yes, yeah.
Myths, whatever. I don't know if we want to do it on the recording, off the recording. I can take a couple minutes and just do this, or if we want, we can push it to next week.
Do we have more to talk about on DeepSeek, or?
Well, I think that the two that I mentioned was the multi-token prediction and the more aggressive MOE. And then if you wanted to do a de-hyping session as well.
Yeah.
We could do that.
Yeah.
I don't know.
All right.
Do we have anybody have an opinion? What's the interest in continuing one more DeepSeek week? Or do we want to move on?
Well, it is getting a lot of attention. So I think if we, it might be worth spending a bit more time, personally.
Okay.
Yeah. I mean, I kind of would vote maybe to move on. I mean, again, the interesting thing is you showed Roger this technology and, these other papers. So you can clearly see that there are some smart engineers who were up to date on the literature, and because they had different how long their 8-bit stuff took versus whatever, they couldn't use the baked in, also they had older GPUs. So even if there's like support baked into the latest, they were using some older ones. So, the NVIDIA software didn't support what they needed. So then they had to like handcraft this. But at the end of the day, their dual pipe is not in some way earth-shattering different than what other people already had devised and are doing. And you could say similar things about the mixture of experts. You could say, whatever. So
it's a little bit of a tweak on a lot of existing work.
Yeah, but one of the good side effects of this is that we end up knowing the state of the art, if you may, and end up digging deeper into these micro aspects of designs of LLMs, which if we are focused only on a research paper, then we are looking at a specific sub-aspect of something in particular, versus here we get into building the system and the system engineering, and also going through all the layers that we may not have read about.
So Dave, I had kind of the same sense of, maybe the magic here is that they publish this and they put it out in the open. And that's that's certainly an element. It raised visibility of it. But then, when I was like, there's a blog, a video, I forget what his name was, did a couple of years ago about scaling up, building scaling systems. And then when Ted brought that, the scaling, what's it? I keep forgetting the name, the
chinchilla or
ultra scale, the ultra scale.
Oh,
the ultra scale. It's like, wait a minute, there's guys have been doing this stuff. This might just be we weren't aware of it. A lot of this stuff is really out there, and maybe it's just more, more visible. Maybe it's visible to us. Maybe it's visible to more people now. I also found on Hugging Face, if you follow that down, there's an implementation that they're doing that has a lot of these hyperscale things that are built into a package, which might be a fun dive too, as well. But
yeah. So that's one of the reasons why I was chatting on Slack, and Dave picked up on it. But I had said there's all these myths or fallacies about how amazing DeepSeek R1 is. And I'm not taking anything away from the engineers. They're awesome engineers. Yeah. But there's very little that you can say they truly just invented something new that other people weren't doing.
It's evolution, not revolution.
Yeah.
Okay. I'm going to stop the recording then for now.
Okay.
Yeah.
Thanks.